Welcome back, folks. Looking at another op-amp circuit, we're going to use nodal analysis. And I'm going to add one more little wrinkle, like I like to do. It's my job. My job is to induce thinking. So hopefully all of these videos are making you think a little bit. So we're going to make things a little bit different, not horribly so. You'll do fine. Okay, here's our circuit right there. And we're going to find I out. And that's one of the... That's the wrinkle, okay? I said that we can't make any assumptions about that current, but we can find it. We've got to go find the node voltages first, but we can come back and we can find that current. Okay. It's also a circuit that, I don't know, maybe you can find it in a textbook. I do apologize for the labels. We're going to deal with that. That's a 4K, and that's a 7K. That's what you get when you're pulling notes out of draft form. Anyhow, so it's not a circuit that you're going to find in a textbook. So you might run into it in the wild. I'm not sure. But you have the tools to analyze this circuit. Okay, so we label non-reference nodes. A, B. There's one here, C. And then there's a big one over here. Okay, and we're going to call that D. Okay, we're going to need 4 equations for this. And I see the voltage supply, so that's 1 kVL, and I see the op amp, so that's a 2nd kVL. And that's the beginnings of our plan. Okay, so we're going to write 2 kVLs, one for the op amp, one for the voltage supply, and we're going to have to write 2 kCLs, and we got to figure out where we can do that successfully. But that's going to give us our 4 equations for our 4 unknowns. All right, I was bad. I didn't label arbitrary current directions for my passive elements, but now I did, so there they are. All right, let's write the ones that are obvious. Well, let's write the KVL for A, right? KVL for A, and it's going to be VA minus 0 equals 2. Also known as VA equals 2 volts. Okay, that one was quick and dirty. Look at this one over here. We got to write it for the op amp, and the positive side, let's just go ahead and start doing it. KVL for the op amp. VC is on the positive side, and VD is on the negative side. Okay, so minus VD. And that's equal to 0, and that one's ready to go. So we're halfway there. Look how quick we did that. Okay, the longer ones are on their way, don't worry. We've got to write 2 kCLs. We're avoiding nodes that have a voltage supply connected to them, and we're avoiding nodes that have the output of the op amp connected to them. Okay, so we're not going to write it for A. We're not going to write it for D. We're going to write it for B and for C. So let's go ahead and do that. Okay, KCL for B. I got this current going in, so it's going to be VA minus VB over 4K. Let's see, I've got this current leaving, so it's going to be minus VB minus VC over 7K. And then I've got this current entering, so it's going to be positive VD minus VB over 5K. That's all 3, so that's equal to 0. If you're uncomfortable writing that, really go back and watch all of the nodal analysis videos, because it's the same way we've been writing KCLs from when I first introduced nodal analysis. Okay, a little bit of algebra on that one. I might even let the calculator chew on it a good amount. Chew it on it and spit out the answer, right? Negative 1 over 4K. Negative 1 over 7K, negative 1 over 5K, VB, let's see, where's VC? We got VC over here, so we got plus 1 over 7K, VC, that was the only one there, and VD is only this one, so we got plus 1 over 5K, VD, and that's equal to 0. Okay. I'll take it. I'll let the calculator do that for me. All right, that was the KCL for B. Now we need the KCL for C. That was our last one, right? So I'm looking at it right here, and I can see that I have 1, 2, 3 things connected, but this is the input of an op amp, so I can assume that it's 0. I'm not even going to write it this time. It's in there, okay, but it's 0, so it's going to drop out. So I've got 2 currents. Is this going to be, yep, we're still on the screen. This one's entering, so it's going to be VB minus VC over 7K. This one's leaving, so it's going to be minus VC minus 0 over 10K. And that's equal to 0. So that one's ready to go. Okay, so we've got our 4 equations for our 4 unknowns. We've got to go solve it, find the node voltages, and then once we have the node voltages, we'll come back and we'll figure out how to get I out of that information. If you know the node voltages, you can find any other value in the circuit. Okay, so let me squeeze all this stuff in here and start us out. Okay, so I think it was VA equals something. I'll go look in a second. 0, 0. So that was our first equation, right? Ooh, I'm going to have to fit that in this form. Yuck. VA equals 2. Okay. Nice and simple for that. I'm not going to end these yet because I don't know how far down I'm going. VC minus VD equals 0 was the next equation, so there's no VA, there's no VB. VC minus VD equals 0. Those were my first 2. Now at least we're on the screen, right? I think I'm going to skip. I'm going to come... Oh, I never did the algebra on this. Sloppy, sloppy, sloppy. Sometimes my mouth goes faster than my brain. Anybody else have that problem? So let's get rid of that. Woo! Let's do some algebra. 1 over 7K in front of VB plus negative 1 over 7K minus, well, I got a minus in there, 1 over 10K, and all of that's in front of VC, and now that's equal to 0. Okay, that's a better form. Let's do that one. I like that. Okay, so yeah, this one's just a little smaller, so I think I can squeeze it in the middle of the matrix here. So it's going to be 0, 1 over 7K, negative 1 over 7K, minus 1 over 10K. This gets a little sloppy when you're writing it out, right? This is all one entry in the matrix. There is no VD, and all of that has to be equal to 0. Ooh, now this one. Ready? Going up to this equation. 1 over 4K, negative 1 over 4K, negative 1 over 7K, negative 1 over 5K. One over 7K. This is getting a little cozy in here, and 1 over 5K. And that's equal to 0. Okay, so we put the bottom on these matrices, and let's figure out what's going on there. And we're going to get VA, VB, VC, and VD. Okay, it scales. When you have more nodes, you're just writing one more equation. That's all. That's why I like Mesh and Nodal. They scale well. Some of you may have learned branch. I'm going to talk while I'm entering this. Some of you may have learned branch. You know, if you branch is just not as organized, and if the circuit gets too complicated, it doesn't scale well. You're going to add a lot more equations to it if you want to go figure out what your circuit's doing. Okay, 7K. There's a lot going on here. I'm gonna be really careful at how I enter this, because it feels like I could screw up. But I've been practicing with my calculator. Have I told you to practice with your calculator? I think you should practice with your calculator. You can almost feel when you make a mistake, like I just did. It didn't feel right under my thumbs. boy, this is where, if the circuit gets much bigger, you probably want to use something like MATLAB or Python to do this work for you. Okay, so what I found was I have 2 volts at VA, I better, 1.28 volts for VB, and then VC and VD have to be the same, right? And they're both behind my head. Boop, they're both 751.9 millivolts. Okay, so I'm going to cheat. And there are the node voltages. Okay, that's a good start, but that's not what we're looking for in this problem. We were looking for I out. Okay, let's go figure out where I out is. It's a current. It's not through a single passive component. So I can't use Ohm's law. Because it's a current, I can't use KVL, so I have to use KCL. So now we go back and write the KCL for D, and we write the KCL for D so that we have a new equation for the new unknown that we're introducing. Okay, so I see 1, 2, 3 things connected to the D node. Maybe if I had a load connected over there, that would change this current, but we don't have that drawn. So we're going to use 1, 2, 3 currents to figure out this KCL. So I'm going to write it up here. This is the KCL for D, and now I can write it because I know everything else. Okay, so this current is 0, right? So I'll just say, we'll call it positive, it's 0, right? IO is entering, since it's going to the right, and then this current looks like it's leaving to me, and it's going to be VD minus VB over 5K. That's all of them, so that's equal to 0. Okay, so that's my KCL. I'm going to steal that and bring it down below so that I can plug in some values. Okay, so that's where I got that from. Solve it for IO, right, and we get VD minus VB over 5K. Right, add this whole mess to both sides, that moves over, and the 0 drops out. Okay, so doing that as quickly as I can, VD minus VB divided by 5K. So I get that current is equal to negative 105.26, probably more precision than I need, microamps. All right. So not too bad. It's a op-amp that you probably can't find in a textbook. There's no good formula for it. But we can apply nodal analysis. And if we apply nodal analysis, we get the node voltages. If we have the node voltages, we can find the current flowing here. We picked to the, well, I guess it was stated in the problem from my notes. It's going to the right. We did the calculations. We found out that it's negative, so it's actually going to the left. Okay. So a couple little wrinkles in that. Let's do I think one more op-amp problem, and then I'll cut you loose on some homework. We'll do some in the live show too. And hopefully you're getting more comfortable with this. I'm going to do nodal when I see an op-amp every single time. Even if I think it's simple, I know that I can go through and I know that I can get the right answer. And that's our goal here. Okay. Stay tuned. Good luck.